Okay, so our next speaker today is Wang, who's a postdoctoral researcher at the Department of Bioengineering and Imperial X at Imperial College London. And they're going to talk today about physics-informed synthetic data learning, boosting multi-scenario fast MRI reconstruction with only one model.
Right. Okay, let's get back to the reconstruction part. Yeah. Uh, Hello, everyone. My name is Wang from Imperial College, and I'm very glad to present our recent work about the physics-informed synthetic data learning, boosting multi-scenario fast image MRI reconstruction with only one model. And in this talk, I want to just balance the medical physics, the part, the AI part, and the signal processing part. So I hope it's going to be very interesting for everyone you guys in the medical imaging from different parts of the working on. Yeah. So let's quickly just look around the introduction of the background and deep learning in the fast MRI. So as we know, the MRI scans usually requires a long excision time. So many methods such as fast sampling has been proposed to accelerate it through the like the case-based undersampling. So we can get images like this with very strong artifacts. So many fancy like deep learning or AI methods have been proposed to get the high quality imaging, just like this one, like the full sampling one. So in a very short time, and to enable the patient-friendly scanning. So, however, there's still very big challenges for the AI in the MRI. That is multi-scenario imaging. In the various imaging scenarios, including different anatomies, orientations, contrasts, vendors, centers, and of course the sampling settings. So to solve this very complex task, how to obtain the large-scale case-based training, the case-based, the sensor domain of the MRI, training data sets for AI, and how to achieve the robust reconstruction in different scenarios. So because it's very impractical to collect data sets which covering the old imaging scenarios. So how to solve this? In this work, we just propose physics-informed AI for fast MRI. We call it the PISF to solve this very complex problem mentioned above. So we just divide the method into different parts. First one is the conventional AI. Here, it means like the first row. Can you see? Just like we just use the realistic raw data for the training, and we have to train multiple expert models for different applications, and also definitely have very poor robustness to different the applications. So, and in our method, which called is physics-informed AI, we follow the MRI physics to produce like a digital scanner and to get the very large scale synthetic data for the learning. And then we only train only one versatile model for that, and it has very strong robustness and generalizability, and we can just do the similar task in the for the diagnosis. So let's just first focus on the data generation framework. It's called the physics-informed synthetic data generation. It follows the physics-based forward model in the MRI, and we just divide it into very important 5 key components. First one, the magnitude, the phase, the coil sensitivities, the noise, and of course the undersampling operations, because we are solving the fast MRI reconstruction problem. And to make everything easier, like for training and of course for the network training and the data generation, we just try to reduce the problem dimensionality from the 2D image to the 1D basic signal. So that means we can just do everything easier. And for the data generation, we need to consider to get much more, much diverse data for the network training. So we try to consider the diverse image contrast for the magnitude, and of course the different experimental conditions for the like the phase, coil sensitivities, and noise, and of course the undersampling operations, and to simulate the multi-coil excision, because we always use the multi-coil in the realistic real-world applications. And finally, we get like the 40,000 paired 1D signals for the sufficient network training, and then we can get more like the result after that. And so why it works, I want to say it may be the diverse data synthesis make it works. As we mentioned before, we use the advanced 1D learning to reduce the dimensionality of the solution space. So, and we can see that in this picture, in the 1D signal perspective, we can get much more similar signals to like a synthetic, and of course the realistic data is very similar. And of course, we can use the 1D version. We also get the 2D version of our method. We can see in the different anatomies, our 1D version gets much better performance in PSNR, of course, the visualization here. And we also do the TSNE visualization to find that the orange signals here, you can see the synthetic training data. We can cover most latent features of the target in vivo MRI, that is blue for the cardiac and purple for the brain here. So we can say that it's expected to train the versatile mapping between the images with and without the artifacts here. So next we will just focus on the network design, that is the physics-informed deep on-road network. So our key ideas is like the separate first and enhance then, which means we just want to separate first. Separate first means we train the synthetic data training to get the 1D versatile 1D foundation network first for the general image artifact removal. And next, in the reconstruction stage, we introduce some data-specific 2D k-space enhancement, not like the kernel-based method like Grappa or Spirit, to do the target self-consistency reconstructions to make everything like in the 2D in the 2D space. So, and of course, we just like this one with our reconstruction with some physics operators and the color corresponding to different part of that. So, and I also want to mention that our method can naturally extend to on the sampling in the 3D imaging, so not only limited to the 1D sampling in the 2D applications. So why it works? I think it should be the advanced model design, as we mentioned before. We can see in this picture for the on-sea cardiac MRI reconstruction applications, our synthetic data trained model is very easy. The basic plane model already got very nice performance and outperforms the realistic data trained sort-time method, the DLT and HDSLR in the PSNR. And our advanced version, the final PISF version, plus the adaptive thresholding and plus the adaptive specific enhancement, like I just mentioned before, can get much more better, like 8% gain in the PSNR. So that is how the advanced model design makes it better. So we think that the PIS may be like a sort of paradigm for the reconstruction, because we just use one AI model for the multi-scenario reconstruction. And here we find that the PIS provides high quality images in the multiple anatomies, such as the knee, the ankle, brain, wrist, and the heart, and across different vendors like Siemens, GE, United Imaging, and Philips, and of course different sampling settings here. And we also invite more like the radiologists from like 5 neuro and 5 cardio radiologists to do the image quality evaluation and find that or more image quality steps into the excellent level, like the 4 out of the 5 point for the clinical diagnosis. So in conclusion, we found that the physically informed synthetic data learning decreases the reliance of deep learning on the large-scale realistic data and achieves the generalizable deep learning in multi-scenario fast MRI. And with one trained model, it supports high quality and ultra-fast reconstructions under different scenarios. And also provide interesting insight that is the realistic trained data is not obligatory and can be effectively replaced by properly generated data. And I also want to thank for my collaborators from different universities and hospitals to support this multi-center research. And this paper has been published on the Medical Image Analysis 2025. And of course, beyond the paper, we also do some real-world perspective study on the different scanners. And we found that it also can be stable and reliable reconstruction, like also the spine images for that. All right, thanks for your attention. You can also find more details on our paper and for our GitHub for the demo data or some like the code. Yeah, before I finish that, I want to mention that we are leading the CMR Recon Challenge from the 2023, and which is the largest cardiovascular imaging and cardiac analysis benchmarks. So if you are interested in topic, we can just follow our GitHub to get the data and also, of course, participating in our challenge this year. And we also recently released some like the multimodal database and the reconstruction foundation models for the we call it the cardio MM for the fast MRI reconstruction for the reconstruction. Yeah. And this year, the 2026, we also we're launching a new one, the CMR 40 flow challenge to accelerate the clinical adoption of the 40 flow MI. So you and I also want to you can just join us and to contribute. Yeah. Thanks.